day everyone. So now I'm going to speak about programming of analog to digital converter of ARM7 processor. So I'm going to use LPC2148 as a processor, and let us go to the program. So this is the program for uh, controlling the initializing the analog to digital converter. Basically we have two ADCs in LPC2148. One is AD0 and another one is AD1. So as far as this program is concerned, we'll be using only the analog to digital converter 0. So analog to digital converter 0 has totally 8 channels, out of which AD 0.0 and AD 0.5 is out of reach. The remaining AD 0.1, AD 0.2, AD 0.3, AD 0.4, AD 0.6 and AD 0.7 are the channels that we can access. While in analog to digital converter 1, all the 8 channels are accessible. That is AD 1.0 to AD 1.7. So coming to the program, so the first instruction is the first three instruction is like the assembler directive, that is initializing the special function registers, that is pincel 1 and AD0CR, AD0GDR, so with its corresponding memory addresses. So EQU is the assembler directive which equates this label with this particular memory address. So inside the program we'll be using this label to access this particular address, so that we are not confused when we are writing the program. So coming to the program, the first instruction is LDR R1 comma equal to pincel 1. So what happens after this instruction is the value 0xe002C004 is stored inside R1 register. So the R1 will be having a memory address of pincel 1. So after that I am moving a content 0x15000000 to R2 register, that is using the instruction LDR R2 comma equal to 0x15000000, and then STR means LDR is load register and STR is store register, store from R2 to R1. So here it goes from this side to the right hand side to left hand side, while for STR instruction it goes from left to right. So the content of R2 is moved inside the memory address that is available in R1. That's what is indicated by this square bracket. So inside this I am moving inside 0xe002C004, I am moving the content 0x1500000000. So this particular 15 I am doing it to activate AD 0.1 at P0.28, AD 0.2 at P0.29 and AD 0.3 at P0.30. So these are the main functionality of this 15. Let us once verify it with the pincel registers format. Okay, this is pincel 1, so in which I have made it as 150000. So which means it is you can see pincel it is like 28th bit I am making it a high, and then 26th bit and 24th bit I am making it high. So you can see this is for understanding I have made. So starting from 0th bit up to 31 bit, so totally 32 bits are there in pincel 1 register. So this 8421 represents the weightage of each and every bit. So here the lower side of the register, the LSB side of the register are all 0, while the first digit is 1 and the next digit is 5. So this I have splitted like 1. 1 represents, here it is 8421, so it is 0001, and this is 5, which can be represented as 0101. So 4 plus 1 5. So obviously I am making 28th bit, 26th bit and 24th bit as high of pincel 1 register. Coming to the pincel 1 register, so so 28th bit. So here AD 3 is activated if I am making 29th bit as 0 and 28th bit as 1. So that's what we have seen earlier. Then AD 0.2 is connected to P 0.29 when 27th bit is made as 0 and 26th bit is made as 1. So that is AD 0.2, and AD 0.1 is activated to P 0.28 when I'm making 25th bit as 0 and 24th bit as 1. So this is the explanation for the pin cell register that we have initialized. Then coming to the next register, that is AD0 control register. So AD0 control register, I am moving the content R2 comma equal to 0x012000102. In this case also the same format. 3 instructions will be doing the single job. So here in pin cell 1 I am moving this 150000, and in this 3 instruction I am moving AD0CR with the content 0x012000102. So each and every initialization of the register will have 3 sets of instruction like this. So here we'll have to check what is the significance of 0x012000102. So here I have written for the understanding the first one. This one is for starting the AD conversion, 2 is to make AD converter operational from power down mode, 1 is for starting clock per division, for setting clock per division, and 2 is for selecting channel 1. So let us check the format of AD0 CR register. So this is your AD0 control register, out of which you have this 0th bit to 7th bit to select the channel. So the channel is selected in a format like if I am making the first bit as high, I mean the AD channel 1 will be selected. So the format channel AD0 CR format is like this, you can see. So here if I am making this as 1, this particular bit as 1, AD 0.1 channel is activated, that is the meaning. So for that reason I have made this as 1, so you can see that 2 is available over here. So this is for selecting the channel. The next is clock division. So that is 15th to 8th bit, that is 8 to 15 bit is used for selecting clock division. So this is just for specifying the speed at which your conversion is happening. So possibly this has to be specified as low as possible. If your peripheral is going to be slow, or it is having high impedance analog source, then this clock division you'll have to reduce the clock division so that your synchronization happens correctly. So that is the one that you'll have to do over here. But in our case we are going to do only the simulation, so we'll be giving minimum value as possible. So in this case what I have given, you can see that it is 1. So that is 8 to 15, I have made it as the minimum value as 1. So 8 to 15 it is used for clock division. Clock division I am giving a value 1. Then next is the 16th bit that is used to specify the burst mode. If I am putting 1, it will operate in burst mode. If it is a 0, it is software controlled mode. Now the presently whatever we are going to do is a software controlled mode. After completing this one, I'll be discussing about burst mode also. So software control mode, in the sense at a time a single channel will be activated. It's analog to digital, whatever the analog to digital conversion has happened, the result will be saved inside the register. So that is the software controlled mode. And here the 16th bit I am making it as 0 so that software controlled mode is activated. So that's the reason here the 16th bit has been made to be 0. Then coming to the 17th to 19th pin, this is for selecting number of clocks per bits. So we'll be keeping the maximum value, that is 000, so that 11 clocks per 10 bits will be set as such, so that our precision will be higher. Then the 20th bit, that is reserved, and 21st bit, that is power down mode. So power down mode is like when you're not operating the analog to digital converter, you'll be making it as 0, so that the unnecessary power consumption or power wastage will be avoided. So I mean, in case when you're going to use the analog to digital converter, you'll have to make this bit as 1. So that's the reason you can see the 21st bit has been made 1, and that's the reason you are getting 2 over here. So the next so the next is 22 to 23 bits are all um, reserved bits, so we are not going to change the values of those bits. Then coming to this 26 to 24, uh, uh, 000 means when the, I mean, it's no start. This value should be used when clearing PDN to 0. So when the clearing is happening, then only you'll be using 0000, and 0001 is for start conversion now. So 26 to 24 will have to specify 0001 for starting the conversion of analog to digital converter. So that's the reason 001 has been specified to start the conversion. So the remaining bits is for selecting the edge. So if I am making this 27th bit is 1, so this bit is significant only when the start field contains 010 or to 1111. So from here to here. So in this case, start conversion on a falling edge on the selected capture or match signal will start the conversion. So as of now in the program, we are going to start the conversion by software mode, not by external pulses. So we'll be not activating this one. So we are not concerned about the 27th bit, and 28 to 31 bits are all reserved. So that is out of our concern, and that is the AD0 CR registers concern. Then AD0 GDR, that is global data register. AD0 global data register is the register wherein the presently converted in analog to digital converters result will be available. It might be from any channels. So here so this is the format of AD0 GDR. You can see the 31st bit specifies the done bit, and the 30th bit overrun. Overrun happens if in case two times a result, one result has been uploaded or stored inside the AD0 GDR register, and after that, if the result has not been read into, and if again some other result is being loaded inside the same register, then the overrun bit will get activated. Done bit specifies, done bit will get activated only when the analog to digital conversion has got completed. So this done bit is in 31st bit, and overrun bit is 30th bit, and 27 to 29 is reserved, while 26, 25, 24 specifies the channel of concern. So AD0 GDR, this is confined with only analog to digital converter 0. Analog to digital converter 1 will have global data register separately as AD1 GDR. So here so this 26, 25, 24 will be confined with the channels of analog to digital converter 0. Then 23 to 16 bits are reserved, while the data will be available between 6 to 15 bits of AD0 GDR register, and 0 to 5th bit is again reserved. So this analog to digital converter is a 10-bit analog to digital converter. So there are basically 10 bits available over here for getting the data. After the data has been obtained, so it will be obtained in the form from this 15th bit to 6th bit. So while if you want to make it as a meaningful value, this particular data that has been obtained has to be right shifted 6 times, so that it starts from the 0th bit. So that is AD0 GDR. So AD0 GDR we have initialized in R3 register, then we are reading the content of AD0 GDR register into R4, then LDR R1 comma equal to 0x80000000 I have made, that is initialize the R1 register with 8 in the sense the 31st bit only will be 1, the remaining bits are all 0. Then I am doing AND operation with R1 and R4. So R1 and the obtained results of AD0 GDR will be logically ANDed with each other. Logically ANDing will result in uh, a result only when both the inputs are the same. So I just want to check whether the done bit has got set or not. For that operation, I mean for that checking, I am doing this operation of logical ANDing. So I am moving the content R5 with the value 0x800000 and I am comparing R1 and R5. So I am checking whether the value of R1 after ANDing has resulted in 800000. So that done bit has been set or not, that I am checking using this compare statement. If it is not set, I am using this BNE, that is branch if not equal, to go back to the LDR R3 comma equal to AD0 GDR register, so that again I will be obtaining the result from AD0 GDR register, and I'll be reading the value and I'll be checking whether the done bit has been set or not by this loop. And after the done bit has been set, then I'm reading the content of the same AD0 GDR register into R4. Then I am making LDR R1 comma equal to 0x0000 FFC0. So this FFC0 is the 10 bits that is available in AD0 GDR register. Here you can see 8421 happens to have F, and then this 8421 happens to have F. Happens to have F, and this 84 happens to give you the value C, 8 9A B C. So totally this gives you the value of F, F and C. So the value that is available inside this particular boxes, that is from 15th box to 6th box, is our concern. So we need to extract only the content of these boxes. For that reason, what I have made is I have put the value 0x0000 FFC0 into the register R1. Then what I am doing is I am ANDing the content of R1 with R4. R4 is the content that is received from AD0 GDR register. So when these two are ANDed, whatever the data that is available in the places of between 15 to 6 will be extracted out, filtering out the other bits. So when we are extracting the data, the done bit and the overrun bit or the channels is of a less significance. So we are filtering it out so that only the data is obtained inside the R7 register after the logical ANDing that has been done between R1 and R4. So the result is available in R7. So as I earlier said, so to make the data meaningful, what I am doing is I am logically shifting the content of R7 6 times, so that it starts from the 0th bit. So that value I am placing it in R8 register. So this R8 register will have the result as of this first channel is concerned, taken into consideration. So here again going for the channel 2. So this part is for activating the channel 1 and retrieving the data from channel 1, while this part is for activating the channel 2 and obtaining the result in R9 register. Here R8 register will have the result of channel 1, R9 register, here R9 register will have the result of channel 2. You can see that whatever I have done in the this particular area I have copied and pasted. Only difference that I have made is this one in AD0CR, that is the control register. Instead of 2 I am making it as 4, so that channel 2 is selected. So that is the one change. And The remaining things are all the same. So AD0 GDR, that I'll be reading, and I am doing and with 8, so that I am checking that whether the done bit has been set or not. And after that, the contents between 15th and 6th bit, 15th and 6th bit content is extracted. I'm seeing to that the content between 15th and 6th bit is extracted and placed, and it is shifted right 6 times and placed inside the R9 register. So same thing is repeated for AD, the channel 3. So here I'm putting it as 8, that is the only difference, and I'm using R10 for retrieving the data. So this is the basic explanation for the ADC converter program. So here I have made it in such a way that the result that has been obtained in terms of hexadecimal value, I am moving it into a register. So in case in the real-time application, the data that has been obtained has to be converted into its equivalent ASCII code or something, so that it could be represented in the LCD screen. So now let us simulate the program and check. Okay. So in case for accessing the analog to digital converter, we'll have to select this A/D converter 0. So this is A/D converter 0, and here we have this AD0 global data register. In case if you want to access AD0 DR0 specifically, that also can be obtained. AD0 DR1, in this case AD0 DR0 we are not going to use, we are using AD0 DR1, AD0 DR2, AD0 DR3 is accessed. So in case if you want, we can access. As far as this program is concerned, we are accessing AD0 global data register. So here this AD01, AD02 and AD03 is the voltage. Here we can simulate the voltage over here. So for our understanding, I'll make it as 3.3. Since the default value for VREF has been given as 3.3, I'm making this AD01 as 3.3. So we can change the V reference correspondingly. If you wanted to make it as 2 or 1, we can give any value depending upon our requirement. So but there is a limitation. The maximum value that can be given is 3.6 or so. Then AD 0.2, I'll just make it as 2.2, and AD 0.3, I'll make it as 1. So now let me run the program. I'll go by step operation. So individual AD0 CR has been set, and the clock per bit has been set, and clock division has been set, and the channel has been selected. Then now the comparison is happening. So the AD converter is checking. You can see the loop is running again and again, and it is checking until the done bit has been set. Now the done bit has been set, and the value you can see A800 FFC0 has been obtained. FFC0 in the sense like it is the maximum value, because I have given AD01 as 3.3. 3.3 is the maximum voltage, so FFC is the maximum. So FFC has been obtained, and that value has to be processed. So now processing happens, and after processing, R8 has the value 3FF. 3FF is the maximum. So the first channel voltage has been converted to its equivalent digital, that is 3FF. So here we can check what is the maximum value. Obviously 10 bit of maximum value has the maximum hexadecimal value as 3FF. So the first channel's operation is completed. Coming to the second channel, now second channel initialization goes on. Then after that, again the done bit is being checked. Now the done bit has been set, so the value has been obtained is AA8. So again this AA8 has been shifted towards the right, and the result is stored in R9. So 2AA is the value that we have obtained for the voltage 2.2. Then now coming to the third channel. Third channel, again the same procedure continues. So again in this case also, uh, you can see that your AD0 DR3 is loaded with 4D8, and when it is getting uh, um, right shifted 6 times, then the R2 register will have, sorry, R10 register will have 136 as the value after it has been right shifted, so that it gives a meaningful value. So 136, 2AA and 3FF is the result for this program in the sense for the channels 1, channel 2 and channel 3, wherein the voltage has been specified as 3.3, 2.2 and 1. So this is concerned with analog to digital converter in software control mode. In case analog, okay, so now we'll discuss about how to um, program the ADC in bust mode. So already we have discussed how to program the ADC in the software control mode. Now we'll be getting into bust mode. Bust mode basically is like we can activate as many channels as possible, and at the same time it will go for running and giving out the result whenever we go for changing it. But as far as the software control mode is concerned, in each and every time it has to be activated so that new value is obtained. So this is the ADC bus mode program. So pincel 1, it is the same value as given in the ADC for software control mode, that is 0x15000000. So that is for activating AD 0.1 to P0.28, AD 0.2 to P0.29 and AD 0.3 to P0.30. And AD 0 control register is the one that is going to change as far as when it is compared with ADC in software control mode. So here we are making the values as 0x00 So the 2 is to make AD converter operational from power down mode, and 1 is for setting bust mode, and this one is for setting clock division as minimum as possible, and E is for selecting channels 1, 2 and 3 at the same time. As far as the previous program is concerned, we will be selecting each and every channel for that particular conversion has to happen in that particular channel, but in this case at the same time all the channels are made active. So let us see the format of control register. So here this is the format, and we can see that 24th bit, 21st bit and 16th bit and 8th, then third, second and first bit are set to 1. So what is this signify? Let us once again look into the ADC control register. So from 0 to 7th bit it is for selecting the channel. So here the 0th to 7th bit we are going to select the channel 1, channel 2 and channel 3. So that's the reason we have made it as E. Then coming to this 8th bit, it is specifying the clock division. As I have mentioned earlier, this should be as minimum as possible, so I am making it as 1 over here. Then coming to the next bits, that is like 9th to 15th bit. So I mean ninth to 15th bit, obviously it is like it is a part of this 8th to 15th bit. So since we have made the 8th bit as 1, so this is the whole bits between 8th to 15th is happens to be 1. Then coming to the 16th bit, that is the setting the burst mode. So in the previous case we have made it as 0, so that software controlled mode is activated, but in this case we are making it as a burst mode. So 1 in the 16th bit represents the program operates in burst mode, so that is over here. So the 16th bit is set to 1. Then coming to this 21st bit, so this I mean 17th to 19th bit, I am making it as 11 clocks per 10 bits, and 20th bit is reserved. So 21st bit I am making it as 1 to activate the AD converter from the power down mode to power on mode. So that is the reason the 21st bit is made to be high. And then coming to this 24th bit, 24th bit is 0 actually. Yeah, so 00211010E. So 24th bit is not active. So because like we are not going to give the start conversions when burst mode is active, there is no start conversion is required, so automatically it will be always in live mode. So 24th bit we have made in the ADC converter in software controlled mode. We have used this start conversion now, but we are not going to use it for this burst mode, so we are ignoring that. So that's the reason we have made it as 0. And the other bits, that is the edge, or this 28 to 31, 28 to 31 is reserved, while this edge we are not going to specify, as we are not going to give any external signal for starting the conversion. So we are making those bits as 0. Then coming to this process of reading the data. So as I have made in the previous case, the same algorithm has been followed, but the register that has been used over here is AD0DR1. So in the previous case we were using AD0 global data register, here AD0DR1 specific data. So AD0DR1 will be connected with unlock to digital converter 0.1. So always the data that is obtained over here will contain only the value that has been converted by the channel 1 of AD0, that is unlock to digital converter 0. So that value I am reading, then I am putting a value 0x80000 into R1 register. Then I am comparing the R1 content with R4. R4 happens to have the value that has been read from AD0DR1 register. So this is for ANDing, I mean, and after doing the AND operation, I'll be extracting only the 31st bit, and I'll be checking whether the 31st bit has been set high or not by this compare instruction. So compare, when I am making it as R1 comma R5, 8 is compared with the value of the result that is obtained in R1 register. So if the 31st bit is 1, then 800000 will be the result. So then it will come out of the loop. Otherwise it will be running in the same loop unless and until the done bit is set to 1. So when it has been set to 1, then I'll be reading the content from the AD0DR1 register. Then I am moving R1 with the value of 0x0000 FFC0, and I am doing AND operation with R1 and R4, and the result I am storing in R7. So this we have discussed earlier, the FFC0. So here this FFC happens to have the result, the total result of the total results of the unlock to digital converter. I mean AD0 DR1 and AD0 GDR has the similar kind of architecture, only the channels will not be available, but the data will be available between the 6th and 15th bit of AD0 DR1 register. So we are going to extract the content of content between 6th to 15th bit of AD0 DR1 register. So for that reason I have made it like 0x0000FFC0, that I am adding it with the content that has been uh, read from AD0 DR1 register. After the reading is over, the content that will be obtained between 6th and 15th bit is right shifted 6 times, so that it gives a meaningful value. So that value, what I am doing is I am storing inside a memory address. 40000 is a memory address that I am storing in R11. The result obtained in R8 register, I am transferring it into R11, the address specified in R11. So the result that has been obtained from here will be stored inside 40000. Then coming to this second one, so I have repeated the same operation here. You can see AD0 DR2, that is the result from channel 2. So wherein I am checking whether the done bit has been set high. If the done bit has been set high, then the result obtained in the AD0 DR2 is extracted and right shifted 4 times. Then the result is stored in 40004. The same thing is repeated with AD0 DR3. The data of AD0 DR3 is read into R4 register, so it is compared with the 0x80000, so that I'm checking whether the done bit for this AD0 DR3 has been set. If it is set, then I am reading the content, then I am storing the value in 40008. So this is the ADC in bust mode. Now let us check how it works. Check. So I'm making it as 3.3. So now we can see that the value that is corresponding to channel 3 of analog to digital converter 0 has changed it to 3FF. The same 3FF has been represented as FF03 in the memory address 40008. And here let me change the value of this 2.2 to maybe 1. So 136, that is obtained in channel 2 of AD0, is represented as 3601 over here. So let me change AD01 as maybe 2.2. So 2AA is obtained in AD0 channel 1, so that is represented as AA02 in the memory address 40000. So by this way we can feed any value to the analog channels at any time, that will be automatically converted in this bust mode. So this is the advantage of bust mode. So this is the program that I wish to share with you. Thank you.